3.6, we're going to talk about taking derivatives, finding derivatives when we can't necessarily write y as a function of x. So what we're looking at then graphically is going to be some curve, and we're still going to be interested maybe in finding the slope of the line that is tangent to that curve at a particular point, but it may be difficult, if not impossible, to solve for y in terms of x at that particular point in the graph. Let's just look at an example here, similar to one that was given in the book. Let's say we have a circle x squared plus y squared equals 9. Now everybody recognizes this, I hope, as a circle of radius 3 that is centered at the origin. And it looks something like this. Now suppose that we're interested in finding, again, like the slope of a line tangent to a point at a particular spot on the curve. Maybe at some point right here. Well, if we're interested in finding the equation of a line tangent to some point right here, we have two ways really of solving this one. This one's not that bad to solve for y. So one way we could do this is to solve this for y. Now if you do that, you subtract an x squared from both sides, and what you get is actually two functions, and that makes sense because you can see that this line, this graph, does not pass the vertical line test. So by itself, this circle is not a function, but we can write it as two different functions, either the positive or the negative square root of 9 minus x squared. Now, if we know that the point we want is going to be in positive territory, that's this part up here. So the graph up here, the top half of this thing, is the positive square root of 9 minus x squared. That's the top half of this circle. If you just want to focus on the bottom half of the circle, well, that is, we get the function y equals the negative square root of 9 minus x squared. Now let's suppose we're at this point right here. Let's formalize this a little bit more. We're at the point 2 comma, let's see, if x is equal to 2, 2 squared is 4, 9 minus 4 is 5. So 2 comma square root of 5 is going to be a point on this circle. Now, if that's the point we want to find the equation of the line tangent, one thing we can do is solve for the top half of this circle, because that's the function y equals the positive square root of 9 minus x squared, and we could do y prime. So if we're looking at y equals f of x equals the positive square root of 9 minus x squared, which we would want to write probably as 9 minus x squared to the 1/2 power, then f prime of x is going to be 1/2 times a quantity, 9 minus x squared to the, let's see, 1/2 minus 1 is negative 1/2, times the derivative of what's inside. What's inside here? Well, the derivative of 9, that's a constant, that's 0, minus x squared, the derivative of that is negative 2x. And so if we plug in, let's see, let's formalize this a little bit better. F prime of x, or make it look nicer, I should say, is, let's see, you got a 2 and a 1/2 here, so those divide to 1. We're basically left with a negative x divided by the square root of 9 minus x squared, because that negative 1/2, remember, throws that 9 minus x squared to the denominator, and the square root is the same as 1/2 power. So that means that f prime of 2, the slope of the line tangent at that point, is negative 2 divided by the square root of 9 minus 2 squared, which is negative 2 over the square root of 5. And so it looks like it makes sense. I mean, we have a negative slope here, a negative slope, negative 2 over the square root of 5. Now, the alternate way we can do this then is with what's called implicit differentiation. So I'm going to go back to that original equation that we had for our circle of x squared plus y squared equals 9. Now remember, what I'm thinking of as y is implicitly defined here as a function of x. Y is equal to some function of x. It turns out that it could be two different functions of x and make this equation true. It just depends on which half of your circle you're on. But if we don't want to take the time to figure out which function of x y is equal to for the particular part of the graph we're looking at, or, like I said, in some equations it's going to be impossible to solve for y, we're going to use this implicit differentiation. And we're going to be using the chain rule, again, thinking of y as a function of x. Basically what we're going to do is we're going to take the derivative of the equation, go through and take the derivative of the equation with respect to x. Well, the derivative of x squared, as you guys know, is 2x. Now, this y squared, well, remember, y is a function of x, so I'm going to use the chain rule here. I'm going to take the 2 down, so 2 times y to the first power times the derivative of y. Y is a function of x, and so dy dx is the derivative of that function of x. So I'm going to replace then the derivative of the y function with dy dx. Now the right side is the derivative of a constant, which is 0. And so if I solve this for dy dx, which is what I want to do at this point, we're going to get our derivative, or the slope of the line tangent, at any point on our curve. So let's see, if we subtracted 2x from both sides, we have A 2y times dy dx equals negative 2x. Divide both sides by 2y, and you'll see we get the same formula for the slope, dy dx, that they got in the book, negative x over y. Negative x over y. So now, if we're looking at the point 2 comma square root of 5, dy dx will give us the same thing that we got before. It's negative 2 over the square root of 5. Negative x over y, x is 2, y is the square root of 5. So can we find the equation then of the line tangent to the curve at that point? Of x squared plus y squared equals 9, that's circle of radius 3 at the point 2 square root of 5. Well, we know that our slope, m, is dy dx, evaluated at our point 2 square root of 5, which again is negative x over y, so negative 2 over the square root of 5. And so we can use our point slope form then. We can say that y minus the y value, which is the square root of 5, is equal to x, our slope rather, negative 2 over the square root of 5 times the quantity of x minus 2. So let's see if we can simplify this a little bit. We'll come up here and distributing the negative 2, we get over square root of 5, we get negative 2 over square root of 5x, minus and minus makes it plus 4 over the square root of 5. So we were not going to make this look too terribly good probably. Y is equal to negative 2 over the square root of 5 times x plus 4 to the square root of 5 plus the square root of 5. But we can still draw a graph here and see how it looks. Let's check that out. So to use WinPlot to draw these implicit graphs here, we're going to go down and see if we can see that. Click on implicit F3, and then we have x squared plus y squared equals 13. We want x squared plus y squared equals 9, and there is our circle of radius 3. Now, on that, we also want to draw the equation of our line tangent, so we'll go to our explicit, and we have y equals, I think it was negative 2 over the square root of 5 times x plus 4 over the square root of 5 plus the square root of 5. If we graph that, sure enough, there is a line that is tangent to our circle in the same direction of our circle, the slope at 2 comma square root of 5 at that point in our circle. So implicit differentiation works and gives us the slope of the line tangent to a curve at that point. Now we'll look at plenty more examples of implicit differentiation, but just want to touch on the next two topics in the book. The next one is orthogonal trajectories. And not really a whole lot here, just to be aware that we can have families of curves that are orthogonal to each other every point that they intersect. At every point that one curve from the first family intersects another curve from the second family. And for example, let's look at number 39, where we have we want to show the given curves are orthogonal. This is going to be more of a specific example. As we said, orthogonal trajectories is when we show that a whole family of curves is orthogonal to a whole family of other curves. But if we look at 39, this will be good practice here. We have 2x squared plus y squared equals 3. We want to show that this curve is orthogonal to x equals y squared. Now what does it mean for two curves to be orthogonal? Well, it means that their slopes are going to be negative reciprocals of one another. So we want to find dy dx here and find dy dx here using implicit differentiation. So we want to find, first of all, dy dx here. So let's go ahead and do that. We're going to use implicit differentiation. We have 2 times the derivative of x squared, which is 2x. Here's the chain rule here. We have y as a function of x, so that's 2 times y times the derivative of y, which is dy dx. The right side we get 0. Let's go ahead and solve this for dy dx. And so we'll see we have a 4x plus 2y dy dx equals 0. So again, solving this for dy dx, we get 2y dy dx is negative 4x. And so dividing both sides by 2y, we get that dy dx is negative 4x over 2y, or negative 2x over y. So there is the formula for the slope of the line tangent to any point on the curve 2x squared plus y squared equals 3. Alright, let's go ahead and find dy dx here, and we should get again a negative reciprocal if these two curves are in fact orthogonal to each other. So here we have the left side. The derivative of x is just, well, it's just 1. So remember, derivative, because we have a slope of 1 here, it's just a linear term. Now on the right side we get, according to the chain rule, thinking of y as a function of x, so we get 2y times dy dx. So solving for dy dx, And when we do that, we get that dy dx is equal to 1 divided by 2y. Now, 1 over 2y is not the exact negative reciprocal of negative 2x over y, but if we look at where these curves intersect, what is the point x comma y where both of these curves are true? Well, one of the points where they're both true is at the point 1 comma 1. In fact, that's going to be the only place these two curves intersect. And at the point 1, 1, what do we have over here? Well, the first curve, dy dx, is equal to negative 2 times 1 over 1, which is negative 2. Whereas this curve here, dy dx, is equal to 1 over 2 times 1 is 1 half. So negative 2 and 1 half are negative reciprocals. If we graph both of these curves on the same set of axes, we'll see where they intersect, and we'll see that they're orthogonal at that point. So plugging them in here on the implicit curve grapher, we have 2x squared plus y squared equals 3 is one of our curves. And let's go ahead and put another one in. So we'll choose implicit. And the second one was x equals y squared. And actually, they do intersect at a couple places. 1, 1, and 1, negative 1. So I misspoke there that 1, 1 was the only spot. But both of these here, you can see if we drew the slopes of the line tangents, the line's tangent here, they would be orthogonal to each other at both of these two places. So we could say here also at 1, negative 1. You can see that if x is 1 and y is negative 1, 2 plus 1 is 3, and 1 equals 1. So those 2 points are where they intersect and where the line's tangent are, in fact, slopes with negative reciprocal slopes that are orthogonal to each other. Last topic then in this section is the derivatives of inverse trig functions, and we're going to use implicit differentiation to find the derivatives of inverse trig functions. Let's go ahead, and they did sine x in the book. Let's go ahead and do the inverse cosine, the inverse of cosine x. Now again, that means if we want y to be the inverse cosine of x, that means we want the cosine of y to equal x. So this is y is the angle whose cosine is x. So y is the angle whose cosine is x. If we take the cosine of y, we get x. And we have to restrict this between actually 0 and pi, because cosine takes on all values. Sorry, y has to be restricted between 0 and pi. Cosine takes on all positive and negative values between 0 and pi, between negative 1 and 1. Alright, so there's our restriction on y. Now what are we going to do here? Well, we're going to differentiate cosine y equals x using implicit differentiation. Remember, we're thinking of y as a function of x here. So we're taking the derivative of cosine y equals x. So the derivative of cosine, remember, is negative sign. So we have the negative sign of y times the derivative of what's inside. Well, this inside function here, remember, we're thinking of y as a function of x. So the derivative of that we'll write as dy dx. On the right side, we get 1. Solving for dy dx, we get 1 over negative the sine of x. Now, on this section where negative 1 over sine of y here, or sine of y. On this section where y is between 0 and pi, sine of y is always greater than or equal to 0. And so, as you remember from your trig days, and so using the identity that cosine squared y plus sine squared y is equal to 1, we can solve this for sine of y. Since it's positive on this range from 0 to pi, it's the positive square root of 1 minus cosine squared y. The positive square root of 1 minus cosine squared y. Now, cosine of y, remember, is the same as x. So we could write this as the square root of 1 minus, instead of cosine squared y, we'll write that as x squared. And so this becomes then 1 over the negative square root of 1 minus x squared. That's what we replace sine y with the square root of 1 minus x squared. So remember y, which represented the inverse cosine of x, the derivative of that with respect to x is now this. So we have this is equal to, we could write it this way, the derivative of the inverse cosine of x, which again is what y was equal to, is the same as 1 over the negative square root of 1 minus x squared. So the derivatives of these inverse trig functions, they will come up from time to time. I don't think you need to memorize them at this point. If I think you do need to, you'll want to do that. The inverse sine and the inverse tangent are the two most common ones that you'll use, and those are ones you probably want to get pretty familiar with, the ones that they derive in the book. So take a look at those. as you already have done, I know, since you already read the book before you watch this video. All right, that's it for this video. We'll look at plenty of examples in the next one.